Hello there, ATS EVS 105 students. Dr. Shragi here. I'm really sorry about the technical problems that we've been having. So let me just go ahead and record this lecture. What I'm going to do is I'm actually going to record the whole thing, but I will in the email message have told you where to jump ahead in this video if you want to skip the part we've already heard and just be continuing where we left off. Alright, so anyway, we're moving through Chapter 2 of the IPCC manual, and as I mentioned, Chapter 2 is long and has lots of different topics like rainfall and pressure and storm tracks and constituents of the Earth's atmosphere and so on. But for the purposes of today, I just want to talk about temperature. As I said in our little lecture there, it is the quantity that's most directly affected by the addition of greenhouse gases to the Earth's atmosphere. We don't worry about exactly how... there can be other changes about things like precipitation, for example, but the addition of the greenhouse gases doesn't directly cause the changes in precipitation. It's the changes in the temperature distribution around the world that will change things like storms and so on. So it's the one most directly affected, and it is also the one that we have the best available data for. We have had liquid in tube type thermometers since the invention of them by Daniel Fahrenheit back in the late 1600s, early 1700s, something like that. And as I said in the lecture, that means that literally 300 and some odd years often we have observations at like European centers of learning. Although they may not be all that well cited and so on. They may not have been so good yet about taking observations in the shade and so on. But we certainly have some kinds of information to go on before then. And really starting in about the 1830s, 1840s, European explorers were remarkably diligent at establishing weather stations pretty much everywhere they went. Certainly by like the 1850s, there's surprisingly widespread coverage of surface meteorological stations, especially thermometers, pretty much anywhere there's European influence, because they've sailed a ship in there and declared it, in the territory of the King of Belgium or something. And as we'll see when we do chapter, I think it's 5, we also have these paleoproxies that can give us information about the climate of the past from things like coral reefs or ice cores or sediments on the floor of the ocean. These things can potentially extend our understanding of the climate back millions of years. And certainly on the order of a few 100,000 years, we actually have a surprisingly good understanding of what the global mean temperature was at any given time and so on. So we actually have surprisingly good information of what is most directly affected by climate change, by the addition of greenhouse gases and so on. Now, as we talked about on that very first lecture, it is actually difficult to quantify climate in terms of the actual so-called absolute temperature. Rather, we tend to work in terms of temperature anomalies, but again, we went over that pretty thoroughly in the first lecture as to what a temperature anomaly is. Alright, so we talked about where these surface observations are coming from. The book, Chapter 2, actually talks about stratospheric temperatures and upper tropospheric temperatures and so on. Let's just dwell for a moment just on surface temperatures at surface weather stations, because I always annoy students with the difference between in situ observations and remote sensing temperature observations. Make sure you're clear about the fact that in situ observations are the kind of measurements that are taken where the instrument is touching what it's measuring. Thermometers are the classic example of that. Scales, rulers, things like that. They touch what they are measuring. And that's in contrast to remote sensing, where the instrument doing the measuring doesn't actually come into any kind of contact with what it is measuring. The classic examples of that are things like x-rays at your dentist's office or telescopes. But a really good example of meteorology is going to be radar systems, and in the case of climate, we're talking about satellites. Satellites are going to have ways that they can make inferences about the temperature at the surface of the Earth, as we're going to see. If we just focus on official government-run weather stations in the United States, I showed you this plot during the original version of the talk that got interrupted by Skype problems. But every place on this plot where there's a red dot is where either the Federal Aviation Administration or the National Weather Service runs an official weather station. There's about 40 to 50 of them working in the state of Nebraska. They tend to be at airports, with only a few exceptions. For example, the official National Weather Service office in Valley, Nebraska, which is just about, 5-10 miles west of Omaha, is not at an airport, but most of them are. The FAA runs them for flight safety reasons. And, like I said, there's a few thousand of them nationwide. There's a few dozen of them in Nebraska. And each of them features a cluster of meteorological instruments that are typically situated someplace in a fairly open area, away from runways, but still on the grounds of the airport. They are generally designed to take observations once an hour, and they measure things for the National Weather Service or the FAA, like winds at a specified height above the ground. They measure the visibility, which is one of the main reasons why the FAA wants them at airports. I remember I told you that that's actually not the Stevenson shelter. I should have fixed that before I reshot this video. That is actually the laser salometer that is measuring the heights of the clouds. Over here, more toward the corner here, is where there was actually the shelter that is measuring the temperature. But we showed you what these shelters look like. I mean, the right word is Stevenson shelters. They are like a louvered box that keeps the official observations of the temperature in the shade. A thermometer is strictly speaking measuring its own temperature. But if the thermometer is in the shade and air is flowing over it, the thermometer will be at the same temperature as the air. If the thermometer is in the sun warms the thermometer at materials of the thermometer itself, like the mercury and so on, at a different rate than it does the air around it, and so you're measuring the temperature of the thermometer, not the temperature of the air. So official National Meteorological Services type observations have to be taken in the shade. Professionals come in routinely to keep these observations calibrated. I tried very hard to find online their actual schedule. I think it's on the order of weekly. They come through and calibrate these instruments, but it may be slightly more, it might be slightly less. I'm not entirely sure how they make their schedule. And they come in and they professionally calibrate these pieces of instrument, adjust them to take external factors into account to allow comparison to others. They make sure that the observations read exactly 0 Celsius when the thermometer is stuck into ice water, things like that. And this technician's job is to make sure that those observations are as precise and as accurate as possible. Now, those are official National Weather Service and FAA observing stations at airports, but like we talked about in class, there's a surprisingly large network of these so-called cooperative weather observers. They are taking daily observations, not hourly observations the way an airport does, and they just record, well, primarily what they record is the high temperature, the low temperature, and the precipitation that fell in the last 24 hours. Some of them are equipped with slightly fancier things and so on, but just to give you a sense, I showed you this plot in the first part of the lecture there. There's a few, this is a little chunk of east central Nebraska, and even here you can see there's a few hundred, there's at least 100 or so observations being taken. At the present time, there's about 600 of these stations operating in Nebraska. There's thousands of them in the United States and tens of thousands of the kind of stations worldwide. That's an awful lot of data coverage. There's an awful lot of good information coming in from these cooperative weather observers. Now, I was able to find the documentation online as to how they keep these instruments calibrated and how they make sure that they have high-quality observations and so on. And we talked a little bit about this, about how there's very specific ways in which you have to keep these thermometers sighted and calibrated and so on. I've got a thermometer at my house, and it's just sitting up against the side of the... I put it on the north side of the house, so at least it's in the shade, but it's just up against the bricks of the house. It seems like it never is in very good agreement with what the app on my phone says the official temperature is here in Evansville. And that's just because the sighting is actually really important to make sure, sighting, as in where the thermometer is sighted, where it is very important. You can't just stick the thermometers on the roof. That used to be a very common way to do it, but that's not the way it can be done. It has to be over level terrain, it has to be earth or sod that is typical of the area around the station. If you're in a desert location, then it needs to be over sand and rocks. If you're in the middle of a corn, surrounded by cornfields, it needs to be over the corn, not over the farmyard, for example. It has to be at least 100 feet away from extensive concrete because concrete absorbs sunlight at a different, it warms up in a different way than the surrounding countryside does. All attempts have to be made to avoid where rough terrain or air drainage or whatever have proven to result in non-representative temperatures. That's especially problematic in the mountains where cold air at night can come flowing down the mountain and so on. You have to keep it away from areas where water tends to stand. You don't want it to be like in a ditch where every time it rains it's surrounded by water. That stands there for a few days or something like that. That would make its temperatures not very representative. Same with drifting snow. You don't want it to be in an area where snow tends to drift, and then days after most of the snow has melted, your thermometer is still surrounded by bright white cold snow. Okay, that would not be very representative of what the temperature is actually doing at your location. There's other restrictions here about like which way the instrument should face if it's still in a shelter that has a door. And what I brought your attention to here is that over the range of the temperatures that are the most realistic, like that's the ones that the temperatures are going to be most often in, these thermometers have to be calibrated to within plus or minus 1 degree 90% of the time, or 95% of the time. In other words, 19 out of 20 of your observations are going to have to be within 1 degree of the true temperature at that location. That's just a measure of how calibrated the instrument is, or well sighted and so on. That's not spectacularly accurate. Official National Weather Service and FAA observations are calibrated more precisely than that. I forgot that I left this slide in here that shows some information that like National Weather Service ones have to be calibrated in facilities to within 0.4 of a degree and so on. But the point is, the actual Weather Service observations that come from like airports and stuff are reported to 1/10 of a degree. They're clearly much more finely calibrated and much more precise and accurate than those extensive but somewhat extensively deployed. I mean, there's hundreds of them in Nebraska, but less well calibrated thermometers that are at co-op stations. With the co-op stations, it's a combination of an issue of just the expenses. A higher quality thermometer would be too expensive to deploy at literally thousands and thousands of stations. And also there's issues of like just the fact that it's being maintained out in the field. Well, it's just out in the field, no one's professionally maintaining it. They are routinely sent back to a facility where they are calibrated in a cold room and so on, where they are chilled to very precise temperatures, and then they calibrate the thermometer. Just to give that beginning of that paper that I showed you, this is actually what a modern cooperative weather observing station min-max thermometer, max-min temperature system, and MMTS looks like. It's not quite so explicitly like a birdhouse the way those Stevenson shelters were, but you can still see it's a white box with louvers and air flows through it. It is not actually a mercury in glass type thermometer that's in there the way old school thermometers were. It's actually digital. I showed you the passage in here that actually says that the aging volunteer corps was finding the thermometers hard to read, which is totally amusing. But anyway, so this is what a modern one of these looks like. I certainly know a fair number of people. You may know I grew up in rural Nebraska, and I certainly know my fair share of farmers and stuff like that. And so I know a lot of people, well, not a lot, quite a few people who do this. They get a little bit of training, and then they pass a test or something, and then they get issued these things. And they take observations routinely, and they're usually farmers or somebody like that, who this is just something they do to serve the public or whatever. Just to give you a sense here, here is an old Stevenson shelter next to an MMTS, the littler shelter that is the modern one. These two are co-located as part of how they verify that there's no that these stations stay calibrated and so on, that they don't, as they age, they don't become less accurate or something like that. Anyway, it's a facility in Colorado State where they're doing that. All these observations are coordinated by the World Meteorological Organization, which oversees the work of all of the different national meteorological services around the world. Whether you're in Afghanistan and we're talking about the Afghan Met Authority, or whether you're talking about Australia and you want the Bureau of Meteorology, or you want Austria at the Central Institute for Meteorology and Geodynamics, every country on Earth from A to Z has its own national meteorological service, including the United States, which calls ours the National Weather Service. And all of them are accountable to the World Meteorological Organization to provide data of a certain quality. The World Meteorological Organization gathers the observations that come in every hour from airports and ships and satellites and all these different sources of information, and immediately relays them over the so-called global telecommunication system to facilities all around the world. It says Washington there. The permanent storage of them is actually in North Carolina. There's also a facility in Australia and a facility in Russia, and then many smaller facilities around the world that also store data. This system relays the data so that literally within moments of an observation being taken, anywhere in the world, it is available to scientists, researchers, government agencies, etc. Partly that's because they need that observation. They are using incoming data to produce the forecasts of what's going to be happening in the weather in the coming days and so on. But from a climate perspective, part of the story here is preventing tampering with the data. Obviously, there's always issues of people are saying, well, meteorologists are just faking this, or this is all some kind of hoax or something like that. Well, part of what we're doing here is making sure that couldn't happen. If you wanted to fake the data, if you wanted to hack into the National Climatic Data Center in Asheville, North Carolina, and start just adding little numbers to all the temperatures that come in each day to show that the world is getting warmer, almost immediately it'd be apparent that something is wrong. The observations are in many different hands. Discrepancies would become immediately apparent. If the archive that's in Russia didn't match the one that was at North Carolina, it would not take scientists very long to figure that out. Okay? This is just part of making sure that they can disarm the argument that scientists are somehow faking global warming or whatever. As we were talking, this is actually the slide that we were at when Skype finally gave up on us today. So if this is where you want to start, that's fine. The World Meteorological Organization makes sure that the observations meet very specific standards. They have to be taken at a very precise time of day. So, for example, if you are supposed to be taking the 9 o'clock in the morning observation, it can't be 9:10, it can't be 9:30, it can't be 9:45. It is 9 o'clock. In fact, it's a very specific time. It's 8:50 for the 9 o'clock observation. They run 10 minutes ahead. Never really have understood exactly why that all is. But they take it at a very specific time. I mean, if you're supposed to take the 9 o'clock observation and you sleep in and take it at 9:30, the temperature is going to be higher. There's been 30 more minutes of the surface warming up. Okay? So they have to be very specifically, very precisely timed as to when those observations are taken. They're taken under very specific controlled circumstances. The World Meteorological Organization specifies the exact shade of white that the Stevenson shelter needs to be painted, and how big the louvers need to be, and how much airflow has to be able to go through per second, and birds and wasps and stuff tend to make their nests in those things, how often they're cleaned out, and all that kind of stuff. Very, very precisely controlling how these things are done, the exact tolerances to which the instruments have to be calibrated and so on. In fact, I believe they actually approve particular models of thermometers and barometers and so on that manufacturers produce as, these are to good enough tolerances, you can use them for your meteorological organization, for the weather service of Nigeria. I mean, you can buy these because they are a high enough quality. They have to make sure that the data undergo quality control. This is literally as in making sure that the data are entered into the system correctly. In most developed countries, the observations are actually entered into the databases automatically. No human ever never typed in the observation that it was 34 degrees last hour in Omaha. It went straight from the digital thermometer into the database without ever being entered, but that doesn't tend to be the case outside of the developed world. They tend to write the observations down and then go to the internet cafe and go to a secure website run by the WMO and enter the observations. Well, if they typed in that it was 17 degrees in Nigeria today when it was really 71, okay, they would use Fahrenheit anyway, but whatever. That would obviously be a big error, right? So there's quality control measures that make sure that the observations make sense and so on. Well, when I looked at a map like this that showed like the June 2009 temperature anomalies, you can see that there are temperature anomalies at sea as well. And we don't really position weather stations at sea, although we do have ways of gathering in situ observations at sea as well, one of them being buoys. There are meteorological buoys and oceanographic buoys out there at sea that have highly calibrated meteorological instruments on them that measure things like the winds and the heights of the waves and the sea surface temperature and the air temperature above the ocean and so on. All these kind of meteorologically interesting parameters. We do have to send ships out there to calibrate them. In fact, my college roommate, that's what he does, is he works for a government agency that goes out and services the buoys at sea, looking for, keeping them in calibration and so on, keeping them in good working order. A buoy at sea is a maintenance nightmare. It gets covered with salt, birds land on it, ships at sea hit them, big like cargo ships and stuff, they just run them over. They don't steer to avoid the weather buoys. there are, several hundred such buoys at sea. Some are drifting and some are moored, where they're tied with a chain to the bottom. We'll learn about more details about that in coming days. But we have a fairly good observation network of those things out there. I mean, it's not spectacular, but we have such things. We also have merchant ships. People at sea on cargo ships routinely take observations, typically every 6 hours, and radio them in. This is done as a standard practice on a cargo ship because good meteorological observations lead to better forecasts at sea, and cargo ships and so on don't in general want to sail into a storm, not because it was poorly forecasted. So at any given time, a fairly large number of ships are out at sea that are reporting. We don't send ships out at sea just to go take weather observations. These are ships that are already on a cargo route, from one location to another, and they are taking observations as they go along. This is 24 hours of observations from that network. Just to give you a sense here, you can kind of see these little streaks there on the plots there. That's what we're, over a 24-hour period, that ship reported maybe 5 times or something like that. So you can see, I mean, it's restricted to sea lanes. It's got pretty good coverage in the North Atlantic and the North Pacific, but, South Pacific, the Southern Ocean, not so much. They are high-quality observations, whether they come from ships or from buoys or from National Weather Service stations or FAA stations, or whether they come from cooperative weather observers, but that doesn't mean there can't be problems. And the main problem we have to be watching out for are inhomogeneities in the data. Inhomogeneities are when something abruptly changes. We can see that the temperatures used to be one way, and then all of a sudden they're a different way. Like maybe up until some time, the temperatures tended to be, the January temperatures in Omaha tended to be right around 32 degrees, and the monthly averages or something, and then all of a sudden the monthly averages was like 35 instead. What happened? Well, for example, we could be worried about changes in instrumentation. When we replace one thermometer with another, perhaps there's a difference in the way they were calibrated. That can result in all of a sudden one fine day we swap out the thermometer and the temperature seems to be different at that station. More problematic are changes that are a little bit gradual, like changes in urbanization or in land use. If a weather station was built out in a cornfield, that is, let's say some little airport, Millard, that's a good example. Millard Airport in Omaha, little airport on the southwest side of the city. Almost certainly there was almost nothing around Millard Airport when it was built. Now it's completely surrounded by city. The changes in the land use and the urbanization around it have changed the temperature at that station over a period of time. That is an inhomogeneity in the data. We're not saying that like global warming is happening at Millard, it's just a change in how humans are using the surface. That's a different set of problems than like greenhouse gases. Could potentially still be a problem, but it is a different problem. In general, techniques exist. There are statistical techniques that can detect inhomogeneities in the data and correct for those problems. Generally speaking, they can be these kind of problems can be documented, and then we can make corrections for them. In another class, I talk about an example where, like, maybe I'm studying, as an African meteorologist, I'm studying data from some particular weather station, and I look through historical data, and I see that all of a sudden in 1982, the humidity starts going up at this station in sub-Saharan Africa quite a bunch. Well, gee, it looks really strange. Why would all of a sudden the humidity be higher now than it used to be? Well, I might run down and, the databases that store things like when did they replace the equipment that measures the humidity. And if I can't find anything there, maybe I would get historical maps and see, oh, look, right around 1982, they built a reservoir next to my station. Okay, it used to be very dry around there, and now there's a reservoir. Okay, these kinds of changes have to usually be documented, but once you know them, there's actually well understood statistical techniques to correct for these kinds of inhomogeneities in the data. All of that so far has been in situ stuff. There's also the remote sensing ways of measuring temperature. This is not a course in remote sensing. Remote sensing is pretty cool stuff, using things like satellites to measure cool properties of the Earth system. But just kind of the broad story here, we're not going to be using radar or any other remote sensing technique here. We're just using satellites. And what satellites do, we'll talk about this more in coming weeks, but, the surface of the Earth emits radiation. It's made of matter, it has a temperature, it emits radiation. And the amount of radiation that it is emitting is determined by the temperature. So the temperature determines how much radiation the surface is emitting. Well, if a satellite can fly by and measure the radiation that is coming up from the surface of the Earth, it should be possible to figure out, based on how much radiation there is, what the temperature of the surface underneath it is. Now, if you've had a class in remote sensing, you know it is way complicated. How to actually do that is an enormous amount of math and a whole lot of physics and so on, but in general, it can be done. In general, meteorological satellites can be used to do more than just take pictures. They can be used to do things like compute the surface temperature, or the temperature of the lower atmosphere, or the water temperature over the oceans, and so on. And that's where maps like this come from. I mean, look at this glorious plot of a particular day's remote sensing observations of sea surface temperature as it particularly happens. Oh my goodness, there's all kinds of wonderful squiggly details in here, little eddies in the ocean and so on. Well, we're not seeing that from buoys. The buoys are 500 miles apart. All these little details come to us from satellite data, where the satellite measured radiation coming up from the surface of the ocean, and based on how much radiation there was, the satellite was able to infer what the water temperature must be. And you can see there's all kinds of wonderful details in here. You can see the Gulf Stream coming up the east coast of the United States. You see this cold little phenomenon here off the coast of Mexico, it's extending into the Pacific. That is a wind event known as a Tehuantepec. It is a type of inertial oscillation, by the way, for people who know about such things. This is a papagayo over here. That's another kind of wind event that happens across Central America, and it's mixing up the surface of the ocean and bringing colder water from down deep to the surface. But we can do this. Now, satellites. Satellites have been up there in orbit for, well, we first started launching them in the 60s. We started having meteorological satellites in the late 60s, early 70s. But it really wasn't until the late 70s that there was a real effort to coordinate this archiving of this data and the quality control and so on. But certainly since about 1978-79, the so-called FIGI year, the first GARP Global Experiment, I forget, it's a big acronym. Ever since that roughly 78, 79, observations from satellites have been pretty good. We have actually a pretty good understanding of what the surface temperature of the Earth was pretty much everywhere based on satellite data. It doesn't mean that there can't be inhomogeneities in satellite data too. For example, orbital drift in the satellite can change the exact time of day at which it's passing over a location. So like if it used to pass over this location at, let's just say 10:30 in the morning, and now it passes over at 10:35, well, I don't know how much I think the temperature has increased from 10:30 to 10:35, but it's probably real. It probably could actually be measured that there's been a drift in the temperatures at that station with respect to that. There could be changes in the calibration on the instruments on the satellite. Astronauts don't go up and catch the satellite and fix it. If a satellite gets out of calibration, we have to figure out ways to fix that from the ground, typically just by applying corrections to the data. Most satellites can turn their imagers and their sensors and so on to face away from the Earth towards known targets, like the moon or particular stars where we know exactly how much radiation is coming from that star or from that full moon or whatever. And they can use that to calibrate the sensors on board, and then they can turn the satellite's cameras back down towards the Earth, or the imagers, or the sensors, or whatever, and that way they kind of can stay in calibration. So maybe once every month or something they turn and they recalibrate the instruments. But it's a challenge. Keeping satellites in calibration is always a factor, is always a concern. But as long as scientists know that there's a problem, if we can identify, hey, the sensor on board this satellite seems to be off by this amount, and some scientific research can be done to show it, and we can verify why it's happening, as long as we know there's a problem, it can be corrected. Okay, we can always fix it in the data on the ground. So if we have all these great sources of in-situ temperature observations and satellites for at least the last 35 years or so, it sounds like we should have some pretty good handle on what is going on with regard to surface temperature around the Earth. So I stole some pictures from the IPCC AR5 Chapter 2. And this is just global temperatures over land. This is just land, not ocean just yet. And we have several different data sets here that have been processed in different ways, which is part of what the AR5 is talking about, the fact that there's these different sources. And you can see that there is a little discrepancy from one to the other, but actually, certainly through most of the period, they're in pretty good agreement. And you can definitely see that, boy, temperatures over land are really climbing. Now this only extends to about, 2012 or something like that, when the AR5 first came out. We know that, like, for example, 2015 would have been the warmest year on record and all that kind of horrible stuff. But we definitely see a big temperature change. It looks like the temperature change has been on the order of maybe 1.5 degrees Celsius over the period of record here. You can see that most of the temperature change occurred since about 1950 or so. Okay, just to give you a sense here, we have the same sort of data from over the ocean. Now, over the ocean, again, there's different archives. The Hadley Center has two different ways of figuring out the sea surface temperature. The ICE, I forget what each of these acronyms stand for actually. But anyway, there's different data sets that record the global sea surface temperature. And you can see actually starting in about the 1940s, they all are in pretty good agreement. And in fact, if you forget about that one that's the blue dashed line, ICODES or something, which I have to admit I don't know what ICODES is. If you forget about that one, actually they're even in pretty good agreement back to the 1850s of the global temperature. And again, now the scale is a little different on this one, but we can see that the oceans have warmed, you know, not quite a degree over that last 150 years or so, degrees Celsius. That's an awful lot of heat to make that happen. In fact, if we switch and take a look at a slightly differently formatted plot, this is the temperatures of each of the decades, so that we're not so distracted by every little wiggle of the lines here. And so going from the 1850s, 1860s, all the way up to the early 2000s here, we can see that there has been a general upward trend, and that upward trend, as we get towards the 70s, the 80s, the 90s, gets very, very dramatic. The temperatures are warming dramatically in the last like 40 years or so. The temperature difference is getting to be, it's almost a ½ degree Celsius warmer than the 1961 to 1990 average, which was already a warm period compared to the 50 years before that or something like that. If we go back to looking at actually a global mean, this includes both the ocean and the atmosphere, both the ocean and the land, you can see that the total temperature change over this 160-year period is somewhere on the range of, I don't know, not quite 1 degree Celsius. I think the figure they tend to throw out is for the last 100 years to be right around 0.7 degrees Celsius. Wow. That could be a lot. I think we're going to have to take some time this semester to figure out if that's a big temperature change or not. But it certainly looks dramatic on the diagram, okay? And I'm going to say it is dramatic, but we'll have to get there. Just to give a sense here, this is of the global distribution of such things. Your Chapter 2 of your IPCC manual actually had several of these kinds of diagrams in there. This one just happened to be the one that was most filled in. This analysis from this service over a 112-year period shows the temperature change. Okay, well, globally over that period we would expect the temperatures to have changed about, a degree Celsius or so. But you can see that there are individual areas where the temperature has changed quite a bit more than that. In fact, that purple color is 2.5 degrees Celsius, which is about 4 degrees Fahrenheit. That's an awful lot of warming that we're seeing up there, like over the Arctic and Hudson's Bay and Siberia, also parts of West Africa and so on. There are a few places on Earth that are getting cooler, most notably the North Atlantic in this particular analysis. But overall, this doesn't look so good. This looks like an awful lot of warming. If I just pulled in a kind of a summary figure that I got from a different textbook here, if we just base it on the surface in situ observations here, we definitely can see that there's a trend. We put the 5-year running average on there just to make it clearer, and you can definitely see that obviously over the period there's been some trend. Again, there are ways to statistically measure the trend, determine its statistical significance, and so on, but that's not really where we're going with this right now. Part of what is convincing that there's an awful lot of global warming going on is that the last decade was the warmest on record. In fact, I stole these figures from Washington Post or Los Angeles Times, I can't remember. Washington Post, I think. The darker red boxes over here toward the end, the pillars over here, those are the 10 warmest years on record, and all of them except one have been since the year 2000. The only one before 2000 was 1998, and that was the year of the mega El Nino event where much of the ocean was so warm. We know from a previous lecture that if we had, this is until 2014, if we had 2015, it'd be almost, like 0.3 of a degree higher than that tallest bar. This is not so good. This looks really, really bad. The trends are actually pretty big. The full trend over the whole period from 1880 to 2014 is at a rate of 1.17 degrees Fahrenheit per century. But the shorter period, more recently, it's a little bit smaller, only like 1 degree per century. Part of the reason why the most recent period has a little bit less of a trend has to do with 1998, which is that last really tall bar before we hit the year 2000. If that weren't there, the trend would be bigger. But because the beginning of that more recent period has that unusually warm year here, we get a smaller trend. You might have heard about like global warming pause and things like that, where like there was a thought that the global warming may have slowed down for a while. That's what they're talking about here. If you kind of just figure the statistics starting in 1998, because 1998 was such a freakishly big year, warm year, it makes look like there's no trend for a little while. But it's not real. It's just that there was an unusually warm year due to an El Nino event in the ocean in 1998. All right. It just works out, by the way, 1.17 degrees Fahrenheit per century works out to 0.65 degrees Celsius per century. You could also write this in per year if you wanted. Some of the figures in the textbook are remarkably inconsistent. They tend to switch between degrees Celsius per decade and degrees Celsius per year, degrees Celsius per century, degrees Celsius over the full record of 112 years. It's frustrating. Okay, you always have to read the captions on the IPCC report. It's important to notice that there's actually two periods in which the warming seems to have mainly occurred if you look at a global level. There seems like there was one big period from about 1910 to 1945, but then from like 45 to maybe 1975 or so, there really wasn't much of a trend. But then starting in 1976 to present, we have some pretty accelerated warming. There's different reasons for this. Part of the story about why they think this has to do with a phenomenon known as global dimming. You might have heard of global dimming. The idea was that for a period of time there was so much burning of coal, and in particular cheap, dirty coal, that was easy to get to at that time, which we've since pretty much mined away. Well, that coal put a lot of aerosols in the atmosphere that reflected a lot of sunlight. And so less sunlight was getting to the surface of the Earth. Yes, we were warming the Earth by the enhanced greenhouse effect, but we were also reflecting more sunlight away by global dimming. And it wasn't until we really started depleting those sources of particularly dirty coal and increased regulation that said they had to, not emit so many aerosols, that by about 1976, that counter effect of the global dimming was actually counteracted. I will leave it to you to decide. We'll learn more about global dimming later in the semester. The global warming has not been very uniform. Most of it is in the northern hemisphere, which is the solid line on this diagram here. Especially in recent decades, almost really the vast majority of the warming has been north of the tropics in the northern hemisphere, and in particular in the Arctic. In this particular analysis, which goes from 1950 to 2014, those red colors in there, they're 0.5 degrees Celsius per decade. Okay, now that's important to keep track of here. The global average was 0.68 degrees Celsius per century. This is in units of degrees Celsius per decade. 0.5 degrees Celsius per decade is 5 degrees Celsius per century. Now, the observations don't go so far back here, but 1950 to present is, that's only about 50 years, so that's about 2.5 degrees Celsius of warming in the last, 50, 60 years. Wow, that is a lot of warming in a place that it's not such a good idea, as we'll see when we study the cryosphere. I won't get all bogged down on the exact plots of the satellite data. There certainly are lots of such plots in your IPCC report, and I happened to grab this one from a different textbook. But suffice it to say that over the roughly 30 years that we have, 35 years that we have satellite data of the surface temperatures, they're in remarkably good agreement with surface observations that are in situ. And that is actually a really, really strong confirmation of the reality of this warming trend. If the satellites were saying, they're independent of what the surface observations are. The teams that are running those satellites don't check to make and adjust their values so they match what the surface observations are saying. Excuse me. That is a separate, independent data archive. And if they're making the same, having approximately the same trends and showing the same temperatures over a period of time, that's a really strong sign that we've probably got we have strong confirmation that the global warming is real. So what did our friends at the IPCC Assessment Report number 5 tell us about all of this? What was their verdict? Well, I'd like to actually copy some verbatim text from what they said in Chapter 2. They said it is certain that global mean surface temperature has increased since the late 19th century. Certain. What is certain in life? Well, the IPCC reports have definitions of what they mean by things like virtually certain, likely, highly likely, probable, unlikely, terms like that. They're all defined. They're in footnotes at the bottom of the page. Certain is not a term that is defined for whatever reason, but virtually certain is a term that they have defined, and virtually certain is 99 to 100% probability. This is more than that. Okay, certain means there is no question, nobody can doubt this here. It is certain that global mean surface temperature has increased since the late 19th century, and they came up with a linear trend showing the warming they came up with the idea of 0.85 degrees Celsius over the period of record. Notice that they were very scientific about it and actually put error bars on it. There was a high probability that the true rate at which the planet is warming is between 0.65 degrees Celsius and 1.06 degrees Celsius over that period. That's really cool, okay? A rate of warming of 0 degrees Celsius, like no temperature change, is not in our range of possibilities. That's important information. It is unlikely that any uncorrected urban heat island effects or land use change effects have raised the estimated centennial, 100-year, globally averaged land surface temperature trends by more than 10% in the reported trend. Okay, that's a hard sentence to parse. That word unlikely is in the footnote. Unlikely means there's a 0 to 33% chance. So it is unlikely, there's a relatively small chance that there are any uncorrected temperature trends, like due to things like urbanization or land use or whatever, that account for more than 10% of the change. In other words, it's not very likely they account for any of it. But if they do, there's only a small probability that it would be more than 10% of the change. Okay, that's pretty solid information there, right? We're really knowing that if there is still some contamination of our surface temperature records, like, stations that are getting warmer and we didn't figure out that it's because of changes in land use, they're saying it's unlikely that's causing more than 10% of the trend that we're seeing. It is very likely that the number of cold days and nights have decreased and the number of warm nights and warm days have increased globally since 1950. Very likely. I looked it up in the footnotes. Very likely means 90 to 100% probability that this is happening. That's pretty solid information. Now, confidence is low for a global scale observed trend in drought or dryness. That's a common idea. People have this idea that a warmer planet is, like the Midwest is suddenly under sand dunes or something like that, and there'll be these big droughts like, California has been in, and so on. Droughts are going to be important, and droughts are going to continue to happen. Is the incidence of droughts, are droughts increasing? Well, this says that confidence is low that there is actually a trend in that. In other words, there's probably not a trend in that. Confidence is an idea in the IPCC that they describe several points in the book as being a measure of agreement among the experts. Okay, confidence is low means that the experts are in general not in agreement. If the experts who have studied this, that are very well trained and know exactly what all this stuff means, are not in agreement as to what's happening, it's not time to be making policy decisions about drought. Well, okay, yes, it is time to make policy decisions about drought. We should all our government agencies should have understanding of what to do and how to manage drought. Understanding drought in the context of global warming is not the right plan at this time. There's low confidence that the incidence of drought is tied to global warming. There we go. There doesn't seem to be any long-term trend in hurricanes. This is confidence remains low for long-term changes in tropical cyclone activity. This is a big, ugly debate in climate science and in tropical meteorology. We do know, as it says here, it is virtually certain that the frequency and intensity of the strongest tropical cyclones in the North Atlantic has increased since the 1970s. Since about the mid-1970s to present, the number of hurricanes, tropical cyclones, per year in the Atlantic has roughly doubled. That's virtually certain. We know that has happened. It's very tempting to say that that has to be due to global warming. If you are a survivor of ATS 113 or tropical meteorology or something, you know that the strength of hurricane formation is related to the temperature of the surface of the earth, the water that the hurricane is moving over. A warmer world should be a world with more hurricanes, or maybe stronger hurricanes, or maybe longer lasting hurricanes, or a longer hurricane season. I don't really know, actually. It turns out no one really knows. We do know that in the Atlantic, starting in about the 1970s, there has been a dramatic increase in the number of hurricanes. But globally, and over the very long term, like the last 100, 150 years, that's less clear. That's an important debate between and within hurricane meteorology and tropical meteorology and climate science that we still are working on. Okay, that's all I needed to show you about this stuff. Now we're going to continue talking next time about Chapter 2, and I hope Skype was working better for us on that day. Please let me know if you have any questions, and thank you for your patience with all of this.